Lecture 7, Network Security Technologies. Theme, Security Technologies and Infrastructure Protection. Technical University of Moldova. Lecturer, Maxim Masayutin, Associate Professor. Introduction. Hello, everyone. Today we're going to explore network security technologies, the tools and techniques that protect data as it flows across networks. This is a vast topic, and we'll cover firewalls, VPNs, intrusion detection systems, network segmentation, and modern security operations platforms. Let me set the context. In the early days of computing, security was relatively simple. Computers were isolated, data was stored locally, and the main concern was physical security. Then came networks, and everything changed. Suddenly, data could flow between systems, attackers could reach targets from anywhere in the world, and security became exponentially more complex. The traditional approach to network security was the castle and moat model. Build strong walls around your network, and everything inside is safe. This model served us for decades, but it's fundamentally broken in today's environment. Cloud computing means your data is no longer inside your walls. Mobile work means your users are outside the walls. And sophisticated attackers regularly breach perimeter defenses. Despite this, network security remains critically important. The network is where data moves, and where it moves is where it's vulnerable. According to the 2025 Cost of a Data Breach report, network layer attacks remain a leading cause of breaches, with an average cost of $4.8 million per incident. We must secure our networks, even as we recognize that network security alone is insufficient. Part 1. Firewall Fundamentals. Let's begin with firewalls, the most fundamental network security technology. A firewall is a network security device that monitors incoming and outgoing network traffic and decides whether to allow or block specific traffic based on security rules. The term firewall comes from construction. A firewall is a wall designed to prevent fire from spreading between sections of a building. In networking, a firewall prevents unauthorized traffic from spreading between network segments. Every firewall makes decisions based on rules. A rule specifies conditions, source address, destination address, port, protocol, and an action, allow or deny. When traffic arrives at the firewall, it's compared against the rules. If a rule matches, the corresponding action is taken. If no rule matches, a default action, usually deny, is applied. Firewall rule management is challenging. Organizations often have thousands of rules accumulated over years. Rules may be redundant, conflicting, or no longer necessary. Regular rule review and cleanup is essential for both security and performance. Packet filtering firewalls. The simplest type of firewall is the packet filtering firewall. This type examines each network packet individually and makes allow or deny decisions based on header information, source and destination IP addresses, ports, and protocol. Packet filtering firewalls are fast because they only look at headers, not content. They're implemented in nearly every router and operating system. The Linux IPtables and Windows Firewall are packet filtering firewalls. The rules for packet filtering are typically expressed as access control lists, ACLs. A rule might say, allow TCP traffic from any source to destination 192.168.1.10 port 443. This would allow HTTPS traffic to a web server. The limitation of packet filtering is that it has no context. It cannot understand the relationship between packets. It cannot tell if a packet is part of an established connection or a new, potentially malicious request. It cannot examine the content of the traffic. This makes it vulnerable to various attacks that packet filtering simply cannot detect. Stateful inspection firewalls. Stateful inspection firewalls, also called stateful firewalls, address the context limitation by tracking the state of network connections. When an internal user initiates a connection to an external server, the firewall records this in its state table. Return traffic is then allowed because it's part of an established connection. This is much more secure than packet filtering. Without stateful inspection, you would need to allow all traffic on high ports above 1024 because you cannot predict which port a server will use for its response. With stateful inspection, you can allow only traffic that's part of connections your users initiated. Stateful firewalls also understand protocol behavior. They know that a TCP connection starts with a SYN packet, followed by SYN-CK, followed by ACK. Packets that violate this sequence can be dropped as invalid. Most enterprise firewalls today are at least stateful. The additional processing overhead is minimal on modern hardware, and the security improvement is substantial. When we talk about firewalls in an enterprise context, we generally mean stateful firewalls at minimum. Application layer firewalls. Application layer firewalls, sometimes called proxy firewalls or application proxies, go further by understanding application protocols. They don't just track connection state. They understand HTTP, FTP, SMTP, and other protocols at the application layer. An application layer firewall acts as an intermediary. When an internal user wants to access a website, they connect to the proxy. The proxy inspects the request, ensures it's valid HTTP, applies content policies, and then makes a separate connection to the external server on the user's behalf. The response follows the same path in reverse. This deep inspection enables powerful security capabilities. The firewall can block specific URLs, scan for malware and downloads, inspect encrypted traffic with appropriate certificates, and enforce detailed policies about what users can access. It can detect and block application layer attacks that packet filtering and stateful inspection would miss. The downside is performance. Deep packet inspection is computationally expensive. Application proxies must parse and understand complex protocols. For high-volume networks, application layer firewalls need significant hardware resources. Next-generation firewalls, NGFW. Next-generation firewalls combine traditional firewall capabilities with advanced features, including intrusion prevention, application awareness, and threat intelligence. The term was coined by Gartner in 2009, and NGFWs have become the standard for enterprise perimeter security. Key capabilities of NGFWs include application identification and control. NGFWs can identify applications regardless of port, protocol, or encryption. They can distinguish between Facebook and Gmail, between Teams and Zoom, and apply different policies to each. This is essential in an era where many applications use HTTP port 80 or HTTPS port 443. Integrated intrusion prevention. Rather than deploying separate IPS appliances, NGFWs include IPS functionality. They can detect and block exploit attempts, vulnerability scans, and known attack patterns. User identity awareness. NGFWs integrate with directory services to associate network traffic with specific users. Policies can be based on user identity and group membership, not just IP addresses. SSL and TLS inspection. By acting as a man in the middle with appropriate certificates, NGFWs can decrypt, inspect, and re-encrypt HTTPS traffic. This is essential because over 90% of web traffic is now encrypted, and attackers use encryption to hide malicious activity. Threat intelligence integration. NGFWs subscribe to threat intelligence feeds that provide real-time information about known malicious IP addresses, domains, and file hashes. Traffic matching these indicators can be blocked automatically. The leading NGFW vendors include Palo Alto Networks, Fortinet, Cisco, and Check Point. These products have become sophisticated platforms that often serve as the central point for network security policy enforcement. Web Application Firewalls, WAF. Web Application Firewalls are specialized firewalls designed to protect web applications. Unlike network firewalls that protect the network perimeter, WAFs sit in front of web applications and inspect HTTP and HTTPS traffic for attacks targeting the application layer. WAFs protect against the OWASP Top 10 and similar web application vulnerabilities. They can detect and block SQL injection, cross-site scripting, XSS, command injection, and other attacks that traditional firewalls cannot see. WAFs operate using several detection methods. Signature-based detection matches traffic against known attack patterns. For example, seeing union select in a URL parameter suggests SQL injection. Anomaly-based detection learns normal application behavior and flags deviations. Positive security model, allow listing, defines exactly what valid traffic looks like and blocks everything else. WEF deployment options include hardware appliances, virtual appliances, cloud services, and embedded modules. Cloud WEF services like Cloudflare, AWS WEF, and Azure WEF have become popular because they're easy to deploy and can absorb large-scale attacks before they reach your infrastructure. WEF tuning is critical and challenging. Out-of-the-box WEF rules often generate many false positives, legitimate traffic that looks suspicious. Organizations must tune rules to their specific applications, which requires understanding both the application behavior and the attack techniques. Part 2. VPN Technologies. Virtual private networks extend private networks across public networks, allowing users to send and receive data as if they were directly connected to the private network. VPNs provide confidentiality through encryption and authentication through various mechanisms. VPNs serve several use cases. Remote access VPNs allow individual users to connect to corporate networks from anywhere with internet access. Site-to-site VPNs connect entire networks together, allowing branch offices to communicate as if they were on the same LAN. Consumer VPNs provide privacy by routing traffic through VPN servers, hiding the user's IP address and encrypting traffic from observers. IPSec VPN. IPSec, Internet Protocol Security, is a suite of protocols for securing IP communications by authenticating and encrypting each packet. IPSec operates at the network layer, Layer 3, making it transparent to applications. IPSec has two modes. Transport mode encrypts only the payload of each packet, leaving the IP header visible. This is used for host-to-host communication. Tunnel mode encrypts the entire original packet and encapsulates it in a new packet. This is used for network-to-network and remote access VPNs. The key IPSec protocols are Authentication Header, AH, which provides authentication and integrity, and Encapsulating Security Payload, ESP, which provides confidentiality, authentication, and integrity. In practice, ESP is almost always used because confidentiality is usually required. IPSec uses the Internet Key Exchange, IKE, protocol to negotiate security associations and exchange keys. IKEv2 is the current version, offering improvements in performance, reliability, and mobile device support over IKEv1. IPSec VPNs are widely deployed for site-to-site connectivity. They're well-suited for always-on connections between fixed locations. However, IPSec can be complex to configure and troubleshoot, and it doesn't always traverse NAT devices and firewalls gracefully. SSL and TLS VPN. SSL and TLS VPNs use the same encryption protocols that secure web browsing to create VPN tunnels. Because they use standard HTTPS, port 443, they traverse firewalls and NAT devices easily. Any network that allows web browsing will allow SSL and TLS VPN. There are two types of SSL and TLS VPNs. Clientless SSL VPN provides access through a web browser without any client software. Users connect to a web portal that provides access to internal web applications, file shares, and other resources. This is convenient for temporary access from untrusted devices. Full SSL and TLS VPN requires client software but provides network-level access similar to IPSec VPN. The client creates a virtual network adapter, and traffic is tunneled through the encrypted connection. This provides access to any network resource, not just web applications. The major SSL and TLS VPN products include Cisco AnyConnect, Palo Alto Global Protect, Fortinet FortiClient, and open-source OpenVPN. These solutions have largely replaced IPSec for remote access because of their flexibility and ease of use. WireGuard. WireGuard is a modern VPN protocol that has gained significant adoption since its inclusion in the Linux kernel in 2020. WireGuard aims to be simpler, faster, and more secure than IPSec and OpenVPN. WireGuard's simplicity is remarkable. The entire codebase is about 4,000 lines, compared to hundreds of thousands for OpenVPN and IPSec. This small size makes it easier to audit and less likely to contain vulnerabilities. WireGuard uses modern, conservative cryptographic choices, Curve 25519 for key exchange, Cha-Cha-20 for encryption, Poly 1305 for authentication, and Blake 2s for hashing. These algorithms were chosen for their security and performance. Performance-wise, WireGuard significantly outperforms both IPSec and OpenVPN in most benchmarks. It achieves higher throughput with lower CPU usage, making it ideal for mobile devices where battery life matters. The trade-offs of WireGuard include limited feature set, no built-in user authentication beyond keys, less mature ecosystem, and some enterprise features still in development. However, adoption is growing rapidly, with many VPN providers and enterprises adding WireGuard support. Part 3. Intrusion Detection and Prevention Systems. Intrusion Detection Systems, IDS, and Intrusion Prevention Systems, IPS, monitor network traffic for malicious activity. The difference between them is response. IDS detects and alerts, while IPS detects, alerts, and blocks. Detection methods. Signature-based detection compares traffic against a database of known attack signatures. When traffic matches a signature, an alert is generated, IDS, or the traffic is blocked, IPS. Signature-based detection is effective against known attacks, but blind to new, unknown attacks. Signatures must be updated frequently to remain effective. Vendors release new signatures daily or even more frequently. Organizations must balance the need for current signatures against the risk of a bad signature causing false positives or performance problems. Anomaly-based detection establishes a baseline of normal network behavior and alerts when traffic deviates from this baseline. This can detect novel attacks that don't match any signature. However, anomaly detection requires tuning to the specific environment, and it generates more false positives than signature detection. Protocol analysis validates that traffic conforms to protocol specifications. For example, HTTP traffic should follow HTTP protocol rules. Traffic that violates these rules may be malicious. Attackers often craft malformed traffic to exploit parser vulnerabilities. Behavioral analysis looks at patterns of activity over time. A single failed login might be normal. Thousands of failed logins from one source is a brute force attack. Behavioral analysis can detect slow, stealthy attacks that would be invisible to signature and protocol analysis. IDS and IPS Deployment. Network IDS and IPS, NIDS and NIPS, monitors traffic at network choke points. A sensor is placed where it can see traffic, often connected to a switch span port or network tap. The sensor analyzes traffic and sends alerts to a management console. For IPS to block traffic, it must be deployed inline. Traffic must pass through the IPS. This introduces latency and creates a single point of failure. If the IPS fails, network connectivity may be lost. High availability configurations with failover are essential for production deployments. Host IDS and IPS, HIDS and HIPS, runs on individual endpoints and monitors local activity, file changes, process execution, network connections from that host. HIDS provides visibility that network IDS cannot, such as encrypted traffic content and local file activity. The leading IDS and IPS products include Snort, open source, Suricata, open source, Cisco Firepower, and Palo Alto Threat Prevention. Many NGFWs include integrated IPS functionality, reducing the need for standalone IPS appliances. IDS and IPS Challenges. False positives are a persistent challenge. Security teams may receive thousands of alerts per day, most of which are false positives. Alert fatigue leads analysts to ignore alerts, potentially missing real attacks. Tuning IDS and IPS rules to the specific environment is essential but time-consuming. Encrypted traffic is increasingly problematic. When traffic is encrypted with TLS, IDS and IPS cannot see the content. Attackers know this and routinely use encryption to evade detection. SSL and TLS inspection can help, but raises privacy concerns and adds complexity. Evasion techniques allow attackers to craft traffic that evades detection. Fragmentation splits attacks across multiple packets. Encoding transforms attack strings to avoid signature matches. Protocol-level evasion exploits differences in how IDS and target systems interpret traffic. Keeping IDS and IPS current and properly configured is essential to address evasion. Part 4. Network segmentation. Network segmentation divides a network into multiple segments or subnets, each acting as its own small network. This improves security by limiting the blast radius of breaches and enforcing access control between segments. In a flat network with no segmentation, an attacker who compromises any system can potentially reach every other system. With segmentation, compromising a workstation in the finance department doesn't automatically give access to servers in the data center. Segmentation approaches. VLAN segmentation uses virtual LANs to create separate broadcast domains. Devices in different VLANs cannot communicate directly. Traffic must pass through a router or firewall that can enforce access policies. VLANs are easy to implement and supported by all managed switches. The limitation of VLAN segmentation is that it's relatively coarse-grained. You can separate departments or functions, but not individual workloads. VLANs also don't span data centers easily, which is problematic in distributed environments. Firewall segmentation places firewalls between network segments. All traffic between segments passes through the firewall, which enforces access policies. This provides granular control, but adds latency, cost, and complexity. Microsegmentation goes further by applying security controls at the individual workload level. Rather than segmenting networks, microsegmentation segments applications. Each server or container has its own security policy, and traffic is controlled even between systems in the same segment. Software-defined microsegmentation, offered by vendors like VMware NSX, Cisco Tetrasian, now part of Cisco Secure Workload, and Illumio, implements microsegmentation without requiring physical network changes. Policies are defined centrally and enforced by software agents on each workload. DMZ Architecture. The Demilitarized Zone, DMZ, is a network segment that sits between the trusted internal network and the untrusted external network, typically the Internet. Systems that need to be accessible from the Internet are placed in the DMZ. The classic DMZ design uses two firewalls, an external firewall facing the Internet and an internal firewall facing the internal network. The DMZ sits between them. Traffic from the Internet can reach DMZ systems, but not internal systems. Internal systems can reach both DMZ and Internet, but DMZ systems have limited access to internal resources. DMZ systems typically include web servers, email gateways, DNS servers, and VPN concentrators, anything that needs external connectivity. By isolating these systems, you limit the damage if one is compromised. An attacker who takes over a web server in the DMZ still must breach the internal firewall to reach sensitive systems. Modern variations include multiple DMZ tiers with different trust levels, application-specific DMZs, and cloud-based DMZ equivalents. The principle remains the same. Expose as little as possible to untrusted networks and isolate what must be exposed. Zero Trust Networking. Zero Trust networking applies the never trust, always verify principle to network design. Traditional network security assumes that internal traffic is trusted. If you're inside the firewall, you can communicate freely. Zero Trust assumes that no traffic is trusted, regardless of location. In a Zero Trust network, every connection is authenticated and authorized. A workstation connecting to a server must prove its identity, even if both are on the same network segment. Policies are based on identity and context, not network location. Zero Trust networking typically involves identity-aware proxies that authenticate users and devices before allowing access to resources. Google's Beyond Corp is the canonical example. Employees access internal applications through a proxy that verifies their identity and device health, regardless of network location. Software-defined perimeters, SDP, that hide network resources until users authenticate. Before authentication, resources are invisible. They don't respond to connection attempts. This reduces the attack surface by making reconnaissance much harder. Microsegmentation that enforces policies at the workload level. Even if an attacker compromises one system, Zero Trust controls prevent them from moving laterally to other systems. Part 5. Security Information and Event Management, SGM. SGM systems collect, aggregate, and analyze security data from across the enterprise. They provide centralized visibility into security events and enable detection of threats that would be invisible when looking at any single data source. SGM Functions. Log collection and aggregation is the foundation. SGM systems collect logs from firewalls, IDS and IPS, servers, endpoints, applications, and other sources. These logs are normalized into a common format and stored for analysis and retention. Real-time correlation analyzes events as they occur, looking for patterns that indicate attacks. For example, failed logins on one system followed by successful login on another might indicate lateral movement. Individual events are normal. The pattern reveals the attack. Alerting and notification informs security teams when significant events occur. Alerts can be based on individual events, correlation rules, or anomaly detection. Alert tuning is critical. Too many alerts cause fatigue. Too few miss real threats. Dashboards and reporting provide visibility into security status. Dashboards show real-time metrics and trends. Reports document compliance and support investigations. Executives want different views than analysts, and SGM systems provide both. Forensic investigation support enables analysts to search historical data when investigating incidents. When an attack is discovered, analysts need to understand what happened, when, and what was affected. SGM provides the data and search capabilities for this analysis. SGM Challenges. Data volume is enormous and growing. Organizations generate terabytes of security logs daily. Storing, processing, and searching this data requires significant infrastructure. Alert fatigue remains a major challenge. SIEM correlation rules generate many false positives. Security teams may receive hundreds or thousands of alerts per day, most of which are benign. Real attacks can be lost in the noise. Skilled analysts are scarce. Operating a SGM effectively requires expertise in security, the organization's environment, and the SGM platform itself. Finding and retaining qualified analysts is difficult and expensive. The leading SGM vendors include Splunk, Microsoft Sentinel, IBM QRadar, and Elastic Security. Cloud-native SGM offerings have grown significantly, reducing infrastructure burden but introducing cloud security considerations. Part 6. Extended Detection and Response, XDR. XDR extends the detection and response concept beyond endpoints to encompass email, network, cloud, and other data sources. XDR aims to break down silos between security tools and provide unified detection and response across the entire environment. Traditional security operations involve multiple tools that don't talk to each other. The EDR team sees endpoint threats. The email team sees email threats. The network team sees network threats. Attackers exploit these gaps, conducting multi-stage attacks that no single tool can see completely. XDR correlates data across sources to detect sophisticated attacks. An email with a suspicious attachment, followed by endpoint behavior anomalies, followed by unusual network traffic, tells a story that none of these signals tells alone. XDR connects these dots. XDR platforms typically include native integrations with common security tools, allowing data collection without custom development. Unified data model that normalizes data from different sources, enabling correlation and analysis. Automated investigation that enriches alerts with context, reducing analyst workload. Response orchestration that enables taking action across multiple tools from a single console. XDR can be native or open. Native XDR is provided by a single vendor whose products are designed to work together. For example, CrowdStrike Falcon offers XDR across CrowdStrike's endpoint, cloud, and identity products. Open XDR integrates products from multiple vendors, providing flexibility but requiring more integration effort. Part 7. Security Orchestration, Automation, and Response, SOAR. SOAR platforms automate security operations workflows, enabling faster and more consistent response to security incidents. As attack volume grows and security teams remain understaffed, automation becomes essential. SOAR Capabilities. Playbook automation codifies response procedures into executable workflows. When an alert fires, the playbook automatically executes, gathering context, performing enrichment, making decisions, and taking actions. Human analysts review results and handle exceptions. For example, a phishing alert playbook might automatically extract URLs and attachments from the email, check them against threat intelligence, scan attachments in a sandbox, search for other recipients, and prepare a summary for analyst review. What might take an analyst 30 minutes takes the playbook seconds. Case management provides a structured workspace for investigating and tracking incidents. Cases include relevant evidence, analyst notes, and action history. Metrics track mean time to detect, mean time to respond, and other KPIs. Threat intelligence integration enriches alerts with context from external sources. Is this IP address known malicious? Is this file hash associated with a malware family? Threat intelligence answers these questions automatically. Integration with security tools enables SOAR to take action across the security stack. Block an IP at the firewall, isolate an endpoint, disable a user account, all from the SOAR platform. SOAR benefits and challenges. The benefits of SOAR include faster response. Automated playbooks run immediately. Consistent response. Playbooks don't forget steps or make errors. Scalability. Automation handles volume that humans cannot. And documentation. Every action is logged for compliance and analysis. The challenges include implementation complexity. Building effective playbooks requires expertise. Integration effort. Connecting to all relevant tools takes time, and maintaining playbooks as the environment changes. SOAR is a powerful tool, but requires investment to realize its benefits. SOAR vendors include Splunk SOAR, formerly Phantom, Palo Alto XSOAR, IBM Resilient, and ServiceNow Security Operations. Many SGM vendors have added SOAR capabilities, and XDR platforms often include automation features. Part 8. Cloud Network Security. Cloud environments require adapting network security concepts to new architectures. Traditional perimeter security doesn't directly apply when your infrastructure is in someone else's data center. Cloud Provider Network Security. Each major cloud provider offers native network security services. AWS provides security groups, instance-level firewall, network ACLs, subnet-level firewall, AWS WAF, and AWS Network Firewall. Azure provides network security groups, Azure Firewall, Azure WAF, and Azure Front Door. GCP provides firewall rules, Cloud Armor, and Cloud NAT. These services are deeply integrated with the cloud platform, easy to deploy, and often included in the base cost. However, they may lack features of dedicated security products and create vendor lock-in. Cloud-native security services. Cloud Access Security Brokers, CSB, provide visibility and control for cloud applications. They can discover cloud usage, enforce policies, detect threats, and protect data. As organizations use hundreds of cloud applications, CASs provide essential governance. Cloud Workload Protection Platforms, CWPP, secure cloud workloads including VMs, containers, and serverless functions. They provide vulnerability management, runtime protection, and compliance monitoring. Secure Access Service Edge, SASE, converges network security and WAN into a cloud-delivered service. Users connect to the nearest SASE point of presence, which provides secure access to both cloud and on-premises resources. SASE combines SD-WAN, firewall, secure web gateway, CSP, and zero trust network access in a unified service. Conclusion. Network security remains essential even as the perimeter dissolves. We've covered a vast landscape today, from fundamental firewalls to sophisticated XDR and SOAR platforms. The key themes to remember. Defense in depth. No single technology provides complete protection. Combine firewalls, IDS and IPS, segmentation, and monitoring for comprehensive security. Visibility is essential. You cannot protect what you cannot see. SGM, XDR, and other platforms provide the visibility needed to detect and respond to threats. Automation is necessary. The volume of attacks exceeds human capacity to respond manually. SOAR and other automation helps security teams scale. Cloud changes everything and nothing. The technologies differ, but the principles remain. Apply network security principles to cloud environments using cloud-native and third-party tools. In our next lecture, will focus on endpoint and system protection, securing the devices where users work and data resides. Discussion questions. As the traditional network perimeter dissolves, how should organizations rethink their network security strategy? What are the trade-offs between comprehensive network monitoring and user privacy? How can organizations effectively manage the volume of security alerts generated by modern network security tools? Thank you for your attention, and I'll see you next time. Review questions. Compare and contrast packet filtering, stateful inspection, and application layer firewalls. What capabilities define a next-generation firewall, NGFW? Explain the difference between IDS and IPS, and describe 3 detection methods. What is microsegmentation and how does it differ from VLAN-based segmentation? Describe the purpose of a DMZ and its typical architecture. What are the core functions of a SGM platform? How does XDR differ from traditional SGM and EDR solutions? Explain the concept of SOAR and provide an example of a security playbook. Key terms. CSP, Cloud Access Security Broker. DMZ, Demilitarized Zone. IDS, Intrusion Detection System. IPS, Intrusion Prevention System. IPSec, Internet Protocol Security. Microsegmentation, a security technique that divides a network into isolated segments to enforce granular access controls. Network segmentation, the practice of dividing a network into smaller subnetworks to improve security and performance. NGFW, Next Generation Firewall. SASE, Secure Access Service Edge. SGM, Security Information and Event Management. SOAR, Security Orchestration, Automation, and Response. VLAN, Virtual Local Area Network, a logical network partition at the data link layer. VPN, Virtual Private Network. WAF, Web Application Firewall. WireGuard, Modern VPN Protocol. XDR, Extended Detection and Response. References and further reading. NDSD Special Publication 800-41, Guidelines on Firewalls and Firewall Policy. NESD Special Publication 800-94, Guide to Intrusion Detection and Prevention Systems. NESD Special Publication 800-77, Guide to IPSec VPNs. Zero Trust Architecture. NESD SP 800-207, Cloud Security Alliance Guidance Documents. Vendor documentation for specific products.